Hi guys, so today we're going to talk about Chapter 3, Section 2 to Chapter 3, Section 3, Linear Functions. So for vocabulary, we're going to talk about a linear equation in two variables, x and y. And it is an equation that can be written in the form of y equals to mx plus b, where m and b are constants. When I say constants, I mean any type of number. So for example, we have y mx plus b. We change our m and our b to a number, such as maybe 3 and 7. And so I'm left with y equaling to 3x plus 7. I could also have fractions, such as 1 over 2 x minus 10. These are both linear equations. The only thing that needs to stay the same are my x and y. So in each case, the x and y continuously stay the same. Everything else can change. Let me move to the next slide. So again, suppose you have y equals to 3x plus 7. Identify the m and b. We just did this where you can find it looking at the constants 3 and 7. Those will show you what your m and b are. So how to identify a linear function? Number one, a linear function is a function whose graph is a non-vertical line. So looking at this image right here, we can say this is not a function because it doesn't pass that vertical line test. Therefore, since it's not a function, it cannot be a linear function as well. Another thing that a linear function must have is a constant rate of change. So if we're looking at this chart right here, we see that x increases by 2, then it increases by 6, it increases by 2, adding it equals to 6, and then 6 to 8 is just increasing by 2 as well. On the bottom, we have 9 to 18, that's increasing by 9. We have 18 to 27, which is increasing by 9, and then 27 to 36, which is also increasing by 9. So the linear function, or this is a function that is linear because of the rate of change being constant. Every single time we see these numbers, they are exactly the same. This one is consistently adding by 2, and this one is consistently adding by 9. Now this works for addition and subtraction, but it does not work for multiplication or division. So a good thing to note is does not work with multiplication or division, only addition and subtraction. And the third rule to always follow is that it has to be represented by a linear equation in two variables. So for example, if we look at y equals to 5 minus 2x squared, I'm going to rewrite it in the form where we have y equals to mx plus b. The way I'm going to do that is I'm going to move this number to the opposite side. So I'm going to swap them out. So instead, I'm going to have y equals to negative 2x squared, since this number was negative. And then I'm going to add it with 5, since 5 is a positive number. And so these are still equivalent to each other, so it still works out. Now I'm going to look at these two right here and compare them. So for my y, the y looks exactly the same. But if I look at my x, as you can see, for the x squared, we have a power of 2. And we can't have that because of the fact that mx plus b, the x is power of 1. So because of that, we can say that this is not a linear function because it cannot be written in the form of mx plus b. Now let's try and practice it a little bit. Let me clear my slide. So if I were to look at the following chart, would this be a linear function or not? I'll give you 5 seconds to answer. Okay? So if I move from 1 to 2, I know that I am adding by 1. If I'm moving from 2 to 3, over here I am adding by 1. And if I'm moving from 3 to 4, I'm still adding by 1. If I were to look at the bottom, I see here that we have 16 to 8, and that is subtracting by 8. And remember, like I said before, we do not look at multiplication or division. We only look at addition or subtraction. So 8 to 4, by subtracting, I would get minus 4. And then 4 to 2 is just subtracting by 2. So although the top side is consistent with adding by 1, the bottom numbers for the y-intercept or y-coordinates are inconsistent. They are not the same number that's being subtracted. So because of that, we have to say that our answer is a non-linear function. Okay. Let's try the next one. Over here we have the following image where we have this shown on a graph. If I want to identify if this is a linear function, actually I'll give you guys 5 seconds to try it out for yourself. Okay, so if we were to look at this image, the way that I could check if it is a linear function is number 1, to see if my image has straight points being made. So as I can see, everything is like a straight line. I don't see any like squiggly things in there. And so that is one way of determining if it's a linear function. The other thing that will help me determine that it's a linear function is doing that vertical line test. So if I do my vertical line test, I see that my vertical line only intersects with the image once. Same goes if I were to make a vertical line in other places. You could see that I only get, my line only intersects once with the image. And so because of that, I could say that this is a linear function. Let's try out another one. Now this will be my last one. So identify if the following is a linear function. Okay, so let's check it out. Right now it looks kind of awkward, so a lot of people do believe that it is not a linear function, but let's draw it out so it looks a little bit nicer. What if I wrote down y equals to 3 over 5 times x? It's still the same and is equivalent to this image right here. I just wrote it a little bit differently. In addition to that, what I also can do here is I can add in that 0. And when I do that, if I were to write down y equals to mx plus b, I see that I have a number shown for my m, I have a number shown for my b. I also have the same variables x and y. And so because of this, I can say that yes, this is a linear function. Okay. So let me clear this and let's move on. Okay, so vocabulary, what is the difference between a discrete versus continuous domain? discrete domain is a set of, or let me highlight it so that you know what I'm talking about. A discrete domain is a set of input values that consist of only certain numbers in an interval. So as you can see from this graph shown here, I have a bunch of dots being shown. And the reason why the graph is shown in dots is because they only consist certain numbers. So for example, if I were to buy a museum ticket that would use a discrete domain, because you can't pay for only a third of the price of a museum ticket. Either you pay for the whole ticket or you just don't pay at all for it. The other half is called the continuous domain, and it is a set of input values that consist of all numbers in an interval. And whenever we graph something like a continuous domain, we always see that there is like a line, a connection that forms from it. And the reason why is because it's consistent of all numbers. So for example, if we were graphing eating a cereal bar and like counting the calories, you don't have to eat an entire cereal bar. You can eat maybe a half of it, or maybe 1/5 of the cereal bar, and we can always pretty much make multiple dots anywhere on this line. And so because we can make multiple dots on this line, we just make that line because it's continuous, where any point in that line can be part of the graph. Okay. So, using function notation to evaluate and interpret. We already know what a linear function is now, and what we want to do now is be able to evaluate and interpret the linear function. And so we say that a linear function can be written as f of x equaling to mx plus b. We use our x points right here as our input. And whatever our function is, this is the symbol for the function, and this is what we change our input. So our function's here. And whenever we place an input into a function, we end up with the output as our answer. So just like before when I said that we input an apple into a function, it can change it where the function cut our apples in half, and our output end up being all of our cut apples. So same thing goes for this right here, a linear function. And then if you want to see the rest of the PowerPoint, it is provided here as well. So using a function to evaluate and interpret, we have this example shown right here to evaluate f of x minus 4x plus 7 when x is equal to 2 and x is equal to negative 2. So f of x equals to negative 4x plus 7. Let's start off with the x equaling to 2. So I want to input my 2 into my function. And the way I'm going to do that is by inputting it into my x. When I do that, I have f of 2 equaling to negative 4 times 2 plus 7. And then I simply find my output by solving this equation here. So negative 4 times 2 gives me negative 8 plus 7. So negative 8 plus 7 just gives me negative 1 as my answer. If I wanted to try to find the input of negative 2, I would write down f of negative 2 equals to negative 4 times negative 2 plus 7. When I do that, negative 4 times negative 2 gives me positive 8. Drop down the 7, and so my output ends up being positive 15. So I can write down that when I input positive 2, or x equals to 2, in my function, function, I get -1 as my output. And I could say the same for this one as well, where instead I could erase this where I say when I get -2 instead in my function, I get +15 as my output. Okay. So let me clear this and let's move on. So let's say, for example, you can't see what the question asks. It says to evaluate f of x equaling to 3x minus 2 when x is equal to -3. So I'll give you time to do that. Okay. So if we have f, it's very ugly looking. How about this? We have f, that's better I guess, of x equals to positive 3x minus 2, and I want to input x equaling to -3. So I'm going to replace my x for -3, and so in my equation I do the same thing where I change my x to -3, and I'm left with 3 times -3 minus 2. Last thing is to identify what my output is, and I do that by multiplying the 3 with the -3. 3 times -3 gives me -9, drop down the 2, or the -2, and then I'm left with -9 minus 2, which gives me -11. So my output here would be -11. So hopefully this helps. Good luck.